So here we are presented with a function f of x, and it is factored into n sets of x minus some constant subtracted by 1. And we have to prove that f of x is irreducible. What this basically means is that f of x can be factored into two non-constant polynomials with integer coefficients. This seems pretty hard, but we could use proof by contradiction for a quick and simple answer. First of all, assume that f of x can be factored into two polynomials, p of x and q of x, and also let the polynomial g of x equal p of x plus q of x. Notice that if you multiply p of a sub I with q of a sub I, we will always get -1. And since both p of a sub I and q of a sub I are integers, one of the values has to be +1 and the other has to be -1. This means that the a sub I is a solution to g of x because g of a sub I is equal to 0. Now we see that g of x has at least n distinct roots, one corresponding to each of the n different a sub I, but g of x has a degree less than n, which could only mean that g of x is equal to 0. This way, it has a degree less than n but more than n roots. Since g of x is equal to p of x plus q of x, which is equal to 0, then q of x is equal to negative p of x. Back to our original definition of f of x, we get f of x is equal to negative p of x squared, meaning that the leading coefficient of f of x is negative, which can possibly be true because the leading coefficient of the polynomial is +1. Proof by contradiction has always been a powerful tool in mathematics, where you start off by assuming it is true, and then after some manipulations, you get something absurd, which makes the original claim false. One possible absurdity is that the signs of a function don't match, as seen in this question, and there are many other common contradictions, such as violations of parity or division by 0.